The counter movement jump is an explosive sagittal plane movement, which is a type of vertical jump. It is used as a simple, practical, and reliable measure of the power of the lower body. The counter movement jump can be broken into 4 phases. Preparation is the first phase, where the body prepares for takeoff. This phase lasts 1.15 seconds and begins in an upright standing position, finishing when the athlete has reached the bottom of their squat and arms are at full extension. Second is the takeoff, lasting 0.05 seconds, continuing on with the arms swinging through and the body being propelled upwards. The takeoff phase lasts until the last moment of contact of the feet with the ground. Third phase is flight, beginning as soon as the feet leave the ground, lasting 0.5 seconds. This phase continues as the body is propelled into the air and finishes the moment before ground contact is made. The last phase is the landing, lasting 1.2 seconds. The feet make contact with the ground, the lower body absorbs the impact of the landing, and finishes in standing position. In each phase, there are a variety of essential kinetic and kinematic principles involved. In the preparation phase, there is a pre-stretching of muscles before takeoff. During the downward section of the preparation, there is a change in gravitational energy, causing the accumulation of potential elastic energy. This phase is preparing the body for the eccentric-concentric coupling of the counter movement jump. During the preparation phase, there is flexion at the knees and hips. Optimal angles of these flexions can be seen here. There is also dorsiflexion of the ankles, hyperextension of the shoulders, and eccentric contraction of the quadriceps. During takeoff, there is an increase of both potential and kinetic energy. The accumulated potential energy from the preparation phase is supplied to the muscles to facilitate takeoff. The kinetic energy is providing the speed for the body to continue in a vertical direction. The combination of the kinetic and accumulated potential energy increase the total amount of mechanical energy available, resulting in maximal vertical displacement. The takeoff phase involves triple extension of the ankle, knee, and hip joints, which generates force into the ground, another determining factor in vertical displacement of the jump. There is also flexion at the shoulder joint. This is part of the arm swing, which increases the kinetic and potential energy of the arms at takeoff. The arm swing continues to pull the body in an upward direction as the upward force acts on the trunk at the shoulder. The takeoff is a concentric extension of the quadriceps, which generates a ground reaction force vector directed vertically to create the greatest vertical velocity. If the ground force is not directed vertically, it will affect the overall height of the jump as forces will be directed towards horizontal displacement, taking away from the vertical displacement. Once the body has left the ground, no additional forces can be generated, so there is no potential for any greater vertical displacement. As the body reaches its peak height, potential energy is at its maximum and velocity and kinetic energy are equal to 0. As the body decreases in height towards the ground, kinetic energy then increases and potential energy is lost. It is important throughout the flight phase that the body remains still, as if there is any movement generated, in particular from limbs more distal to the trunk, this would create torques, moving the body away from the linear vertical trajectory, therefore decreasing the maximum height of the jump. During the landing phase, there is a rapid deceleration caused by the quadriceps contracting eccentrically to absorb the kinetic energy that was created throughout the jump. The landing phase involves flexion of the hips and knees, dorsiflexion of the ankles, and hyperextension at the shoulders. The first biomechanical variable that can be altered to improve performance is the arm swing. The arm swing generates the most vertical velocity the closer to 160 degrees it is at takeoff. The arm swing generates energy early in the jump and allows for greater potential energy of the arms at takeoff. You can see in these two videos the difference between a full swing closer to 160 degrees at takeoff and a suboptimal swing. This is something that coaches could focus on to vary performances. The second variable that can be altered to improve performance is the angles of the knee joint. Many studies confirm that the optimal angle for the best vertical displacement is about 90 degrees. The closer the athlete is to this angle allows for increased vertical force and vertical displacement. If a coach is to closely analyze the athlete's knee angle before takeoff, they can analyze whether or not they are generating the greatest amount of force possible and work towards adjusting the angle closer to 90 degrees.